Hello everyone. So my name is Tu. I'm a PhD student at the University of Southern California. And today I'm gonna present a paper that I worked with my college. The paper is addressing resource provisioning and allocation of ensemble in situ workflows. So from the motivation and the background of the work. So this work is motivated by a real world application that is molecular dynamics or MDs. So as you can see on the right, here pictures of a molecular system that has a lot of atoms, and MDs is the computers models that compute the atomic position of the molecular system that evolves over time by observing the interactions of atoms. So MDs offers two advantages. The first one is to control the configurations of the molecular system, and second is to observe the important process of the molecular system. In order to obtain these outcomes, so the analysis of the MDs simulation data is necessary to integrate into the simulation byline to analyze the trajectory that generated by the simulation of the snapshot of atomic position. So now let's see how the MD simulation and analysis pipeline is run on HPC system. So traditionally, the MD simulation will write the entire frames to the parallel file system, and the analysis will be performed post hoc by getting the data from the parallel file system and perform the analysis test later. This type of approach is called post-processing. However, post-processing encounters problems with contemporary computers. So the increase in the computing capabilities of the HPC system easily allow the MD simulation to generate large amount of data. However, the stagnancy in the I/O bandwidth prevents that large amount of data to be able to store efficiently in the parallel file system. So which make the parallel file system become the I/O bottleneck for post-processing. So in order to overcome the I/O limitations, so there is an alternative processing paradigm has been emerged recently, which is called in situ analysis. So the intuition is to analyze the data as soon as the data is generated. So thanks to the iterative manners of the simulation, the simulated data is able to be split into portions to be staged to the analysis over iteration as well. So by doing that, the simulation and the analysis can run concurrently to each other and interleave the execution. So it can help to reduce the time to solution. However, MD simulation nowadays is not only how to run the simulation in a long-term scale, there is the problems that prevents the simulation to reach the interesting molecular events. So in order to resolve that problems, so instead of running a long MD simulations, there is an attempt that take the divide and conquer approach to combine multiple short MD simulation in ensembles and distribute them in a way to increase the probabilities of observing rare events. And by running multiple MD simulations simultaneously, so actually ensemble methods is trivial for parallelization. So that is the reason why we can take advantage of the HPC system to accommodate a series of parallel MD simulation. So this work focus on a class of MD simulation that run ensemble, and because of that we revisit the definition of in situ workflow ensemble. So let's say we have a set of simulation that run in parallels, and each simulation is coupled with several analyses, and every coupling of simulation and analysis will form an ensemble members, and all the ensemble members will form the workflow ensemble. So there are three levels of granularities here. So ensemble component, ensemble members, and workflow ensembles. So we would like to capture the behavior of the workflow ensemble at all those multiple levels. So initially, to characterize the behavior of the workflow ensemble, we utilize a set of traditional metrics. As you can see here, cache miss ratio, or memory intensive, or max span, to be able to characterize the workflow examples. However, we see that using these traditional metrics does not warranty to have a thorough understanding of the workflow example, and it's also not straightforward to gain the insight about the behaviors of the workflow example. So we think that we need a method to be able to do that, and that how in this work we end up to propose multi-state performance indicators to evaluate the performance of workflow example. So what are multi-state performance indicators? So let's say we have an execution of a workflow example with multiple example members. And for each example members, we generate a computational efficiency E with based on one of our previous work that you can reference here. And with this computational efficiency E, we use it to derive the first stage of the performance indicators that represent the resource usage. So resource usage at the first stage characterize how efficiently the resource is utilized for the execution of the ensemble members. And after that, we add on top of the performance indicators another layers to represent the resource allocation. So resource allocation characterize the efficiency of how the ensemble components is located on the set of compute node that allocate for the ensemble members. And finally, is the state of resource provisioning that characterize how many compute node or how many resource the entire workflow ensemble use. And by following that procedures, every ensemble member can generate the performance indicators for that ensemble members. So let's say we have performance in P1, P2, P3 for only ensemble members in the workflow ensemble. And these performance indicators will serve as an input, as the inputs for an objective function. And this objective function is used to allocate the values of the performance indicators into one single values. And we would like to maximize the values of the objective functions to be able to maximize the performance of the workflow example. So, so now let's take a look at the experiments. So for the experiment setup, so we enable a runtime system to be able to couple the simulation and analysis using Situ. For the simulation, we use a medium scale on atom system that has been implemented in Promax. And for the analysis, we use a common analysis that is appropriate for Institute, that is the collective variable computation. And our execution platform is Characterization. And for the experimental result, so we explore several configurations of the workflow example. Each configuration specify the number of compute nodes, the number of example member has in the workflow example, and also the node index to specify how the simulation and analysis is mapped into the set of compute node that allocate for the workflow example. And we focus on the set of configuration that has two example members. And in these 5 configurations, there are 3 configurations that use 3 compute nodes and 2 configurations use only 2 compute nodes. And intuitively, we think that the performance of the last 2 configurations should return better compared to the other configuration. And more specifically, if we take a look at the last configuration, C1.5, so this configuration is where the simulation and analysis of the same example members are co-located on the same node. So this configuration can be beneficial from data locality So we expect this configuration C1.5 should be the best configuration. So now let's take a look at the result that we observe the behavior of the objective function on the performance indicators that we propose in this work. And we focus on the last performance indicators where it gathers all the state that we previously described in the previous slide. And we see that C1.5 actually it has the highest values of the objective function. So the outperformance of C1.5 confirms our hypothesis, and at the same time, it also validates the benefit of co-locating coupled components together. So for the conclusions, so the proposed performance indicators in this work provide capabilities to compare the configuration in multiple resource perspectives. So we can leverage these performance indicators to evaluate the scheduling decision of in-situ ensemble. And by doing that, we improve the resource usage of the workflow ensemble. And at the same time, we are able to improve the simulation exploration by enable high throughput ensemble MD simulation. So now, for the future work, so we plan to apply the method that we propose here into the scheduling problems of the in-situ ensemble. So the conclusion actually wrap up my presentation here. So thank you for your listening. So if you have a question, so I'm happy to take all of your questions.